Neil deGrasse Tyson has shared with the world some unsettling news. It's highly plausible that our universe was born within a black hole, and perhaps we are living inside a black hole, unaware of it until today. Does this challenge the Big Bang Theory, and why this truth points towards evidence supporting the concept of a multiverse? Black holes are objects of scientific fascination. Their existence is beyond doubt, yet no scientist has ever directly observed them because black holes are invisible. They are made up of matter that eludes our eyes, becoming tangible only through their immense mass, which warps space-time. Due to this warping, black holes act like magnets, pulling all nearby matter towards them and swallowing it whole. What happens inside black holes is a scientific mystery. We can only speculate or calculate using the equations of general relativity. Scientists speak of singularities, the concentration of all matter into a single point. Did you know that scientists have theorized that even our universe originated from such a singular point? Scientists have speculated that each black hole has the potential to create an entirely new universe within itself. At first glance, this notion may seem staggering. Let's examine the nature of black holes. When you consider the massive amounts of matter that black holes suck in, stellar bodies, planets, gas clouds, and accretion disks breaking down into their fundamental components, which are essentially energy and information, the proposal becomes logical. Quantum physics teaches us that information, as a fundamental component of matter, can never be destroyed. Now, consider the beginning of the universe as explained by scientists. There is nothing there except potential concentrated at a single point. This tiny point, called singularity, holds all the information needed for the emergence of a fully fledged universe. Scientists envision the end of our universe in various ways. The prevalent and embedded theory suggests that at the end of the universe, giant black holes will absorb all matter and accumulate the informational potential of the entire cosmos. But what happens next? It's unlikely that the universe will remain in a frozen state. Far more probable is a continuous movement, restructuring, and further development. If all matter concentrates in one point, in a massive black hole, where would we then find ourselves? Sir Roger Penrose proposed the theory of a cyclic universe many years ago, a cosmos that is born, expands, ends, and then we are reborn. The latest theory of life in a new black hole takes this idea even further. Information is a fascinating entity in the realm of quantum physics. Upon delving into the nature of information, it's far from guaranteed that, at the end of the universe, all information must be concentrated within one massive black hole for a new universe to emerge. Theoretically, this could occur in all black holes. There are numerous speculations about what black holes truly are. Initially considered to be wormholes or gateways to other dimensions, these ideas persist among enthusiasts of science fiction to this day. Physicists, up to this point, are uncertain about what black holes truly represent. What is clear is that they absorb vast amounts of information and don't return it, at least not within our universe. This is where we get to the crux, as this information must go somewhere if, firstly, it isn't annihilated and, secondly, can't escape the black hole within our universe. Much like a mystical mirror, it's entirely possible that information vanishing here reappears in another universe. Consequently, each black hole in our universe potentially serves as a gateway to a new, separate universe. If this holds true, then we inhabit a multiverse, and black holes might indeed be portals to other worlds. Another compelling piece of evidence supporting this hypothesis is the peculiar mirror reflection of the world outside a black hole and within a black hole. While we don't know much about the interiors of black holes, some quantities can be calculated thanks to Einstein's equations of general relativity. A defining feature of all black holes is the event horizon, the boundary beyond which there is no salvation for matter. Anything that crosses the event horizon cannot return. Now, let's explore together the world inside and outside a black hole, and you'll be astonished. Beyond the event horizon, an object distinctly feels the gravitational pull's intensity. While matter is drawn towards the black hole, an object outside the event horizon might still escape if another force attracts it or if it can accelerate sufficiently to counteract gravitational forces. However, once an object crosses to the other side of the event horizon, no force or acceleration within this universe can free it from the gravitational grip of the black hole. Black holes gain weight through the mass they absorb. This implies that something must be happening inside them that we currently don't comprehend. Let's delve into a few more intriguing quantities. If we consider all known forms of matter and radiation in the observable universe, we have normal matter consisting of protons, neutrons, and electrons. Ghostly neutrinos follow their path, rarely interacting with normal matter. Dark matter, dominating the mass of the universe but eluding direct detection. Photons, particles of light or quanta carrying the energy of any electromagnetic event, and gravitational waves. At present, we can observe in all directions up to a distance of approximately 46 billion light-years. If we now take all the energy and mass of the entire observable universe together, we arrive at the equivalent mass of the universe using Einstein's famous formula, E equals mc squared. Now, let's pose an intriguing question. What if we compress all of this into one point? The answer is the same as if any mass or energy were compressed into a point. At that moment, all the mass corresponds to the sum of all masses. In computational terms, this unified point would then form a black hole. Einstein's theory of gravity describes how mass warps the space around it. The Schwarzschild radius is a term from this theory, denoting the size of a non-rotating and uncharged black hole based on its mass or the distance between the singularity inside and the event horizon. Hypothetically converting all the mass of the observable universe into a black hole, surprisingly, the Schwarzschild radius of this black hole would be almost exactly as large as the observable universe itself. This intriguing coincidence raises the question of whether our universe could actually be an equivalent of the interior of a black hole. Delving deeper into this consideration makes it even more interesting. In the 1960s, scientists made a remarkable discovery. They found pervasive faint radiation coming from all directions in the sky. It resembled the detection of soft light shining throughout the universe. This radiation had a consistent temperature in all directions, approximately minus 270.425 degrees Celsius, slightly above absolute zero. This radiation is known as the blackbody spectrum, and its formation strongly suggested that the newly discovered faint radiation must originate from something uniformly hot. Scientists identified the Big Bang as the hot source of this radiation, known as the cosmic microwave background. Both the radiation and the Big Bang are considered crucial evidence that our universe is expanding and cooling, or that in the past, the universe was hotter and denser. As we travel back in time, everything becomes less homogeneous and compact. If we go all the way back, we approach the singularity, where matter becomes so dense, and the temperature rises to such extremes that the laws of physics we know break down. If we examine the equation describing a black hole, something remarkable happens. The Schwarzschild radius, r, is the distance from the center of the black hole to its event horizon. If we start beyond the event horizon and take the Schwarzschild radius of a black hole as the distance r, we end up at a point at infinity. From this, we can make two conclusions. The distance from the event horizon to the singularity inside corresponds to infinity in the material world. Therefore, a black hole leads to infinity. Moreover, all the properties of space beyond the event horizon of a black hole are identical to the properties of space inside the black hole. If we calculate using the Schwarzschild radius and some other quantities, we get a perfect reflection of external space inside a black hole, or vice versa. The scenario can be likened to taking a sphere that reflects 100%, essentially a perfect mirror. Subsequently, we observe that the aggregate universe beyond this sphere ends up distorted in the mirror reflection, impacting new calculations. These new calculations have spawned an entirely new model of the beginning of the universe, based on this knowledge. Instead of originating from a singularity, it is much more likely that the universe was fundamentally configured in a state of rapid, constant exponential expansion. If this is the case, there must be some field that provided the energy inflating space, and this field could be space itself. Only when it stabilized did the hot Big Bang occur. This would render many theories about expansion and spacetime seemingly implausible, and we'll have to wait and see what further research and observations, including those from the James Webb Space Telescope, reveal. Thank you for watching. See you soon.